Hi guys, your favourite armoured penguin again. Now, today what we're going to concentrate some of the more specific arguments that flat earthers have issued us, and just examine them much closer than the skin deep level that flat earthers never get past. And these ones are more specifically about aircraft. So the first one is that aircraft never dip their nose down to account for the curvature of the earth. My gut response has always been, well, how do you know? Have you spent long periods of time watching pilots fly aircraft? I mean, the fact that they even make this exclamation gives us a good idea that they probably haven't. In fact, it suggests they've never been on an aircraft. Or if they have, they aren't thinking critically about what they are saying. Because let's turn this statement into a question. Do aircraft dip their noses constantly to make up for the curvature of the Earth? And the answer that we get is, well, it's actually more complicated than that. Isn't that convenient? No, it's not. It's a right royal pain in the arse, because, believe it or not, we like simple answers to apparently simple questions. So let's start with how aircraft work. And this, for your reference, explains why planes fly and aren't dragged to the ground like everything else. You can't talk about aircraft without touching on fluid dynamics. Fluids moving at a high velocity have a lower pressure than those moving at a slower pace. And this can easily be explained by taking a pump that produces a steady flow. If we take two pipes, each with a takeoff point, we measure the pressure at that takeoff point. And the easiest way to do this is just if you have your takeoff points upwards vertically. If our pipes are different diameter, remember that we are passing the same flow through these pipes. Our velocity through the larger pipe will be lower, and this lower speed will produce a higher pressure. Air works exactly the same, and this is called the Bernoulli effect. This is part of the principle that aerofoil works on. The underside of the wing is flat, or as near to flat as it doesn't make a difference, whereas the upper side of the wing is actually curved. Now, in high school, this is what we are taught produces lift in an aircraft, and don't get me wrong, it certainly helps. But it's not the only part that produces lift. Aircraft are specifically designed so that, pretty much pointing straight, they will produce lift. So, what this means is, well, we know that the atmosphere thins as you rise in altitude, and there is a point where you will not be able to fly any higher. And we call this the flight ceiling, as it is a physical boundary to the altitude of the aircraft. There is no way to fly higher than this. And even this is only achievable in perfect conditions. So what happens when the aircraft reaches this point? Well, the aircraft starts skimming or skipping at this point. And this isn't a particularly fast or efficient way of flying. So aircraft normally fly below this point. We now know that aircraft have a point where they cannot fly higher. And as I say, this is what stops aircraft from becoming rockets and just flying off into space. So what else might be a contributing factor to the question? Well, contrary to most flat earthers' apparent assumptions, the Earth's atmosphere is not a uniform jelly. The atmosphere has high pressure areas, low pressure areas, it has winds connecting the high and low pressure areas. We also know that these winds can change direction with altitude, and this is exactly what causes turbulence while we are flying. You know that sometimes gut-wrenching feeling that we are being thrown around or even dropped out of the sky. From a pilot's point of view, this means that the pilot, or more likely these days, the autopilot, has to constantly adjust the pitch, yaw, bank of the aircraft, and by much more than the 1 degree every 70 miles that you would see flying at sea level. Although, I hope you can see the issue with flying at sea level. And flying higher reduces the amount of dip needed. So we've now come across two reasons why constantly dipping the nose of the aircraft is not noticeable. And I still have a few more, actually. The most obvious is that due to stresses and strains on the aircraft, wear and tear, constant maintenance, the above weather effect, aircraft are fitted with a way to tighten trim and affect their aero surfaces. Being able to encourage an upward, a downward, a clockwise, an anti-clockwise, a left, a right, to correct for anything that might be stopping the craft from flying straight and level. It would not take much to knock this trim a few notches to account for any relative nosing up caused by the curve of the Earth. In fact, this trim comes in handy when taking into account the imbalance caused by a non-uniform distribution of passengers and cargo, for instance. Lastly, and this is probably the most important, how do you think you'd notice the dipping of a single degree every 70 miles? Do you think you would notice this even if you were watching the pilot the entire flight? Regardless of whether you think it's possible to notice this slight dip, I would suggest you can't. And anyone who can drive knows that even driving down a straight and flat road, you still need to make small adjustments to the steering wheel. And you will also know that 90% of the time your passengers have no idea that you're doing this. Artificial horizons, or attitude indicators, never roll backwards as an aircraft circle the Earth. This is true. And indeed, if you spin a gyroscope, then this is what you would expect. A spinning gyroscope, regardless of its orientation, will keep its orientation relative to absolute space. And this is why if you spin a gyroscope for a whole sidereal day, you will notice it revolve through 360 degrees. But the attitude indicators on aircraft don't. Why is this? When proposed with this thought, allegedly Dave Murphy decided to ask a pilot.
Because I asked the pilot on my last flight, do you ever notice the artificial horizon rolling backwards? He said, no, but the artificial horizon has complex electronics in it to make sure it knows where it is on the Earth and it compensates.
While plausible, this seems a rather elaborate way of correcting for the curve of the Earth, especially for anyone more engineerly minded, and it's obvious that this conclusion wasn't arrived at by anyone with an engineer mindset. This means that either Dave has pulled this out of his arse, or, if we give him the benefit of doubt and accept this at face value, it means that the pilot he asked also isn't an engineer. And, well, why should he be? He's a pilot. Assuming that the word of the pilot should be taken as gospel, and that he knows how every instrument on his panel works, is moronic. I'd wager that 90%, 95%, we'll go with 95% of drivers don't know how their speedometers work. And yes, I do, but none of my friends do. So when he later called the manufacturer of the attitude indicator, and they explained that there aren't any electronics in it.
But I went to the manufacturer of the artificial horizon, and they confirmed to me that it's completely mechanical, nothing electronic in it whatsoever. So it's literally just a gyroscope that can freely move. So that right there is proof to me that planes fly over.
We must have a conspiracy. I shall just point out here that Dave didn't ask the obvious question, and that is, well, how do your attitude indicators make up for the curve of the Earth? No. He asked, do your attitude indicators contain complex electronics that know where they are in the world? I wonder why he chose that question. If he had asked the more obvious question, the answer he would have probably got is this. Attitude indicators used to suffer from horizon progression, or horizon precession, where the horizon would roll back as the aircraft flew further around the world. Noticing that this was a problem, people put their minds to it and found a solution. During aerobatic displays, the high G-forces that resulted from performances could upset the attitude indicators in craft. So to avoid the issue of attitude indicators being inaccurate when it's needed, like, for instance, landing, they added a cage to the gyroscope. Now what a cage does is it slowly bleeds off the angle until the gyroscope realigns with gravity, so that it doesn't point in the angle of the G-forces attained during aerobatics at the rate the bleed is low. I mean, it tends to bleed off at about a degree or two every minute. But this is more than sufficient to make up for the curve of the Earth. So most aircraft now have caged AI, caged attitude indicators. Of course, if allegedly Dave Murphy wanted a real answer, then he could, like I did, spend 10 minutes and a Google search into the phenomena and find the same simple mechanical answer that contains no complex electronics to work out where in the world it is. His argument would utterly fall apart. Alright guys, well I think this one has been a long enough one, so thanks very much for listening. I would especially like to say thanks to Rob, who has come up with my new, flashy, new introduction animation. So thanks for that. And I will see you again for the next Common Flat Earth Misconceptions. Please remember to like and subscribe if you've enjoyed what I've said. And if you've got anything you want to say to me, the comments are below, guys. Yeah, just another quick special thanks to Rob. And you can find Rob either on Reddit. His name is RobSC_16, or on YouTube as RobAllen1216.